Okay, welcome everyone back to our second morning session. Our first speaker is Barak Nehoran from Princeton University, and he is going to tell us something about the general quantum duality for representations of group with applications to quantum money, lightning, and fire. So let's welcome our speaker.
Hi, I'm Barak Nehoran, and this talk is based on joint work with John Basanja and Mark Zhandry. And this paper uses some representation theory, as you can see from the title. But I think our results will be more widely useful to the community. And so in this talk, I'll make sure to introduce anything I use so that everyone can follow along. But first, I want to go back to the basics of what distinguishes quantum information from classical. I'm sure everyone here is familiar, but I want to point out some specific features using an analogy. We can think of classical information like a book. On the other hand, quantum information is like, well, let's say a cake. Hold on, it doesn't quite look quantum. Ah, there we go. Much better. Okay, so going with this metaphor, if we have a book, you can always read it. But with a cake, you can taste it, but it'll ruin your cake. It's a little example of the phrase in English, you can't have your cake and eat it too. You can make copies of your book, but you cannot copy a cake without knowing the recipe, unless you're some master chef, which I'm not. And lastly, you can send a book over the internet, but good luck emailing a cake. Now, these last two are going to be important for this talk. They're called cloning and telegraphing, and we'll come back to them later in the talk. They'll be really important. Okay, so I'll first introduce the main application of our result, which is to construct quantum money, quantum lightning, and a new cryptographic object that we call quantum fire. Then I'll talk about our main technical result, which is a non-Abelian generalization of the swapping distinguishing duality of Aaronson, Atia, and Susskind. And finally, I'll show you how to use it to build quantum money and quantum lightning. I'll start by telling you about money, lightning, and fire, starting with quantum money. As I'm sure everyone here knows, cloning is a task of taking a quantum state to two copies of the same state. And the no-cloning theorem says that this is not possible in general. And quantum money is just the cryptographic instantiation of this, where the states can be viewed as banknotes that cannot be cloned. We have a mint that produces the state. Since the public does not know the state, they cannot clone it. But anytime they want, they can send it back to the bank for verification. So quantum money is fundamental to quantum cryptography, and in fact, it was the first quantum cryptographic protocol, predating quantum key distribution, or wait, rather key establishment, as Gilles told us on Tuesday. There we go. So it predates quantum key establishment by a whole 14 years. And in fact, Wiesner's paper inspired Bennett and Brassard's famous BB84 protocol. And this is called secret key quantum money because only the mint can verify. But of course, this is the disadvantage. So in 1982, in the first published paper on quantum cryptography, they defined a public key version where anyone can verify. Which is to say that there's a public verification algorithm that anyone can run. And this has a tremendous advantage because now it can be used, it can be transferred from person to person. The bank does not need to know and does not need to be involved in every transaction. And quantum money is useful for many applications besides money. Basically, anytime you want something that's verifiable but not clonable. So for example, say that you have the deed to a house. And this is a document that proves that you own the house. And you want to be able to transfer it around and verify it, but you want to prevent the case where two people both claim to own the house. And unfortunately, unlike the secret key version of quantum money, the public key version of quantum money cannot be information theoretic. If you have unbounded time, you can run the verification until it succeeds. And this has been quite a challenge to build. So for this talk, when I say quantum money, I'll always mean the public key version. And now there's one more version of quantum money called quantum lightning. And this is a stronger collision-free version where the security holds even against the bank or the mint, where even they can't produce two copies. This might seem weird because the mint produced the mint just produced the state in the first place, right? So why can't they just do it again? So you should think of each banknote as coming with a serial number, and the minting process is randomized. It applies some kind of measurements so that we'll never see the same serial number twice. And like with public key quantum money, there's a public verification, so this implies public key quantum money, since if the public could clone, then so could the mint. And the name comes from the phrase, lightning never strikes the same place twice, which is not true, by the way. But nevertheless, Mark Zhandry said that quantum lightning never strikes the same state twice. All right, so as I said, over the past 43 years, it's been quite a challenge to construct quantum money and quantum lightning. And this is just a sampling of the attempts that have been made over the years. And in the first column, we have schemes that are merely conjectured, but just have no proof. Unfortunately, many of these have been broken, as you can see in red. So we would like to have a scheme with a security proof. And this can be done in the black box setting, where you don't allow the adversary to see the internal workings of some black box, just the input and output behavior, and then show that it requires an exponential number of queries. But there are no black boxes in the real world, so if you want to actually use these, you have to find a way to instantiate the functionality. And unfortunately, these instantiations are often broken, including some of the ones that are here on the left. So the gold standard is to show a security proof in the plain model, without black boxes, with a reduction to a hard problem. And until this point, the only example in this column has been Mark Zhandry's proof of security from indistinguishability obfuscation. But this is a very strong assumption, which implies almost any other cryptographic primitive, and this post-quantum security is unclear. Also, Zhandry's security proof is only for quantum money, and there's been no such security proof for the stronger quantum lightning security. So we give the first security proof for quantum lightning, assuming pre-action security of non-Abelian group actions. And this is by generalizing Zhandry's scheme from Abelian to non-Abelian group actions. And this is not just merely a surface modification, since this drastically changes what we can prove, allowing us to get rid of the black box of Zhandry's scheme and prove security in the plain model. So now I've told you about money and lightning. I've yet to tell you about quantum fire, which is a brand new cryptographic object. So this quantum fire uses what's called the no telegraphing theorem. So telegraphing is the task of converting a quantum state into a classical message such that it can later be recovered. And like no cloning, the no telegraphing theorem says that this cannot be done in general. And importantly, if you can telegraph, then you can clone by running the second part twice. But cloning does not allow you to telegraph efficiently. And quantum fire is just a cryptographic instantiation of this difference. With a mint that sparks the flame, that anyone can clone. So this is a public cloning algorithm. But the public cannot store it classically. It's efficiently clonable, but not efficiently telegraphable. So this is like an actual flame, where if you can have a flame on your candle, you can spread it around as much as you like, say between the different candles, but the moment that it's extinguished, it's gone, and you cannot recover it. Now, like quantum money, there is also a public key version and a collision-free version, but I won't get into that here. I'll just say that previously, quantum fire was only built with a quantum oracle in a previous work of myself and Zhandry, but it's not clear how to instantiate this oracle. Really, it's not clear how to efficiently clone even orthogonal quantum states without going through the classical description. And we show one way to do this, which gives a plausible candidate with a classical oracle. And later work by Chakan, Goyal, and Shmueli managed to prove the security of a different construction, also using a classical oracle. And Alper will be giving a talk on that later this afternoon, so I encourage you to look out for that talk. So let's go back to unclonability. How do you prove that something is computationally unclonable? So here's the recipe. One way to do this is to have a task that is hard if you have one copy of the state, but easy if you have two copies of the state. Why is that? Well, if you could efficiently clone the state, then just clone it and work with two copies, right? So, one copies and two copies are equivalent if that's the case. So anytime you have something that's hard with one copy, easy with two copies, this necessarily means that it's computationally unclonable. So we need a task like this, And the one that we propose is a task of testing dirty fixed points. So a dirty fixed point of unitary is a state where there's some register that's preserved, almost like an eigenvalue, and also a junk register that just gets messed up. And so it's not quite a fixed point, since the second register is changed. So it's a dirty fixed point. So notice that if it were a clean fixed point, then there'd be two ways to test it. You could use the Hadamard test, where if you have a supposed eigenvector, you could prepare a plus state, and then you apply a unitary controlled on this plus state, and then just check if the plus state remains a plus. Or you could have, if you have two copies of the state, you could use the swap test, where you apply the unitary to one of the two copies, and then controlled on the plus state to swap the two. But now suppose you have a dirty fixed point. So one of the registers gets messed up. So now what happens? Well, if you try running the Hadamard test, you'll get a different junk state on each term. And so the Hadamard test just won't work. But the SOBS test still works. You can just ignore the junk register. Just set it aside and do a swap test on just the registers that you're testing. So the message is that for unclonability, we want the swap test to work, but not the Hadamard test. And testing dirty fixed points is a type of task that achieves that. And we'll later see a specific instance of this. Now, I'd like to tell you about our main technical contribution, which is a generalization of a truly beautiful duality between two computational tasks. And we show that it's a special case of a wider phenomenon that has to do with group representations. So our result is a generalization of the swapping distinguishing duality of Scott Aaronson, Yossi Atia, and Lenny Susskind. And involves two tasks on, let's say, Schrodinger's cats. Or really any two quantum orthogonal states. They don't necessarily have to be cats. So the first is to map a live cat to a dead one, and a dead one to a live one, with the same unitary. So this is called swapping, but not in the same sense as the swap test, because there's no two registers here, just a single cat changing between two different states. So maybe flip is a better name here, because it's like flipping a bit. But they call it swap, so we'll go with that. And the second task is that of distinguishing the two possible superpositions, either a plus superposition or the minus superposition. And they show that these tasks are computationally equivalent. If you have a circuit for either one, you can use it to implement the other with just a constant overhead. And they use it to argue why we can't see Schrodinger's cats, since if there was a superposed cat right in front of you, you wouldn't even be able to tell that was there. Why is that? Because you would at least need to be able to distinguish its positive superposition from the negative superposition. Otherwise, it could just be a classical mixture of dead and alive. And then by the duality, this would allow you to map alive to dead and dead to alive. In other words, you need to be able to resurrect the cat. I think they call it necromancy hard. In any case, this duality has been quite useful for cryptography, since the task on the left is a search problem, and the one on the right is a decision problem, and it's been quite useful for proving various kinds of search decision reductions in quantum cryptography. And once you know about this duality, you'll start seeing it everywhere, though admittedly not always with cats. And in this work, we view it as a representation of the group Z2 of a single bit, either swap or don't, and we show that it's a much more general phenomenon. So the first task becomes a task of implementing a group representation, and the second task becomes something we call Fourier extraction. And I'll tell you about these in a moment, but we show that these two tasks are computationally equivalent. And this assumes that the group has an efficient Fourier transform, which is the case for abelian groups and many important non-abelian groups like the dihedral group and the symmetric group and other groups that are important for cryptography. So let's start with what is a group representation. And if you don't know representation theory, now is the time to pay attention, because we'll start with a basic introduction. This is everything you need to know about representation theory. It's just what's on this slide. So a representation is just a mapping from the group to the unitaries homomorphically. So the function takes a group element G and maps it to a corresponding unitary U, UG. And now we take all these unitaries, we could diagonalize each one, but not all at the same time. not unless they commute. If they don't commute, then the best that we can do, if we want to diagonalize them together, is write them in a block diagonal form, where in some basis they all look like this, with zeros outside the blocks. And for this, you can see that if you start in a subspace corresponding to one of these blocks, then you stay within the subspace, no matter which of the unitaries you apply. And these are called invariant subspaces. And every representation preserves some set of them. And finally, like with diagonalizing unitaries, you can get degeneracy or multiplicity. So for instance, maybe these purple boxes all have the same unitary, and the orange ones maybe have a different one than the purple one. And so we can label them by lambda 1 and lambda 2, and so on. Everyone with me so far? Right. So now the important thing to know is that this transformation, the transformation that diagonalizes it, this is called the Fourier transform. And in fact, this is a definition. You can define the Fourier transform this way. It's the unitary that optimally block diagonalizes the representation. If you've seen other definitions of the Fourier transform, then those are almost always special cases of this one. So if you take a quantum state and apply the Fourier transform, it sends you to a basis state where the representation is block diagonal, and we can index it by 3 labels. First, there's what's called the irrep label, which essentially indicates which unitary appears in the corresponding block. And if the same unitary appears multiple times, then we have an index that runs over the multiplicity. For example, we could be in the second block of the 3 purple blocks. And finally, with each block, we choose some basis, and the state index tells us which corresponding basis vector we have. Of course, in general, you'll be in a superposition over these labels, but if you have a definite irrep label and a definite multiplicity, then I'll just write the state as if it's inside the block. Although, of course, the block is a unitary, and the state is really in the subspace corresponding to it, but it'll be nice to depict it this way, just visually. So as a specific example, we can take what's called the regular representation of the cyclic group, Zn, which is when you take the space spanned by the group elements and you act on them by just normal addition, mod n. So that's the regular representation. And since these all commute, then in this case, you can actually fully diagonalize it, which means that all the blocks are one-dimensional. And they just have these phase terms along the diagonal. And if you take a state like the one here and apply the Fourier transform, then you get the irrep label that is the term that appears in the phase. And there's no multiplicity because there's one of each block. And there's no state index since the blocks are all one-dimensional. And so this here is the quantum Fourier transform that everyone is familiar with from an intro class. This is the standard quantum Fourier transform. And it's just a special case of the general definition. But when defined this way, it's so much more general. But yeah, anytime you want to take the Fourier transform of just a group, then you just apply this definition to this regular representation, in which this regular representation is just defined this way, with just applying the group operations. Okay, so one more example that I'll mention is the one that ties it back to the swapping distinguishing duality, since our goal is to generalize it. So here, the group is just the simplest possible one. It's the group Z2. And the group has 2 elements, the identity and the other one, or just 0 and 1. So to specify a representation, we just have to assign a unitary to each of these 2 group elements. The identity will obviously be assigned to the identity matrix, and the other element will be assigned to the swapping unitary, the one that flips between live and dead. And of course, it's good to check that applying the non-identity element twice brings you back. So swapping twice is the identity. Now, the Fourier transform in this case is just the one that sends the plus superposition to the label that reads plus, and the minus superposition to the label minus. And these are the Fourier basis of the representation. So that's a group representation. And implementing is equivalent to Fourier extraction. So what is that? Well, it's a generalization of a common technique that's used in everything from the swap test to tomography to Shor's algorithm and hidden subgroup problems. It's a generalization of the concept of measuring in the Fourier basis. So ideally, the way that you'd go about doing a measurement in the Fourier basis is to take a quantum state, apply a Fourier transform, copy the measurement into in the Fourier basis, copy it to another register, and then you measure. And we'll also undo the Fourier transform on the main state just so that it's a projection. So the problem is that the Fourier transform of the representation might be inefficient, even when the Fourier transform of the underlying group is efficient. So for example, think back to the swapping representation. The group is as simple as can be. It's just Z2. And the Fourier transform of this group, of the group Z2, is just the Hadamard. But the Fourier transform of the representation of the group, now that involves reversibly converting these weird superpositions over cats into these plus and minus labels, which is clearly a lot more complicated, if even possible. So is it possible to measure in the Fourier basis? Well, yes. It turns out that for abelian groups, the circuit is equivalent to the circuit on the right, which interestingly is essentially the same circuit but flipped upside down. But now instead of doing a Fourier transform on the representation, we're doing a Fourier transform on the group itself, which for most interesting groups is efficient. And this might resemble a circuit identity that's often taught in introductory classes, where if you apply Hadamards to a C-naught, it flips the direction of the C-naught. And in fact, the identity for the C-naught is just a special case of this theorem, where both wires just have the regular representation, or Z2. The regular representation of Z2. And so this circuit on the right is quite common. It's called the Fourier sampling circuit. And as I mentioned, it's useful in everything from swap test to Shor's algorithm. So now, let's see how it generalizes to non-Abelian groups. What happens if the group is non-Abelian? So remember that I mentioned that the Fourier basis can be indexed by 3 different indices: lambda for the irrep label, I for the multiplicity, and J for the state index. And as before, the ideal functionality would be to apply a Fourier transform, copy the representation, and then measure. And like with abelian groups, this can be achieved by applying the Fourier sampling circuit on the right. But now these circuits are not quite equivalent. The one on the right does more than you would expect. And we show that if you take the Fourier sampling circuit on the right and don't measure the third register, the third wire, then if you look at what happens in the Fourier basis, it actually looks something more like this. Now notice that while the irrep label is copied up to the top, the state index J is swapped up rather than copied, which means that it's completely extracted from the original state. So no information about J is left behind. And this is what we call Fourier extraction. If you're familiar with the principle of phase kickback, then this can be viewed as a state kickback, where instead of a phase, it kicks back a whole quantum state into the control register. So in some sense, the Fourier extraction is kind of like the next best thing when you can't quite do a Fourier transform. So to frame it in a different way, imagine if you were able to do a full Fourier transform on the representation. And this is, of course, not possible in general, but we'll see that in a moment. So you first measure the irrep label lambda, which would collapse you down to just these purple subspaces. Then you'd get the multiplicity, which tells you which of the purple subspaces you have. And finally, take a basis for each subspace and measure the subspace completely. And this defines a Fourier transform for the representation. But it's not possible to do in general, since there's no way to distinguish between these purple subspaces. They're all identical under the representation. So what you can actually get is some encoded state that hides the information about the multiplicity. It's still there information theoretically, but not accessible. And this is Fourier extraction. It measures the subspace, really measures just the lambda, and then coherently extracts the encoded state. So what do I mean by that? Well, imagine instead of having a basis state, you had some superposition in the subspace, like this green state here. Then the sum of the superposition would travel all the way to the right register and give you the exact same state. The exact same superposition, but on the first few computational basis states in this register. The way you should think about this is if you have this purple subspace, which is embedded in some higher dimensional Hilbert space. And say you have this green state vector here. You're extracting that same superposition to appear just on its own in the standard basis, the same size as the subspace. Now I mentioned that you can't quite get the multiplicity, since you can't distinguish between identical subspaces. But since we've extracted away the information about the superposition within the subspace, none of that information is left over in the rest of the state, which means that you get what we call an archetype state, which only depends on the subspace. And in fact, it characterizes the subspace. And this is quite important because this is what allows us to get our proof of quantum lightning security. Remember that for lightning security, you have to show a problem that is hard if you only have one copy of the state, but easy if you have two copies. And specifically, we want a case where we can do a swap test, but no Hadamard test. And that's the problem of same versus different subspace. So you either have two different states within the same subspace, or two states in different but identical subspaces, like the two purple ones here. And you have to decide which one it is. And notice that you can't do a normal swap test because it will fail in both cases. They're just different states. Even when in the same subspace, they're different states in the same subspace. But if you can do a Fourier extraction, then you can do a swap test on just the archetype states, which are the same if they're in the same subspace. And so this will pass on the left and fail on the right. So if we have some kind of operation that may or may not move states across these identical subspaces, then this is just an instance of the dirty fixed point problem, where one register, the archetype state, is fixed, and the other one can behave arbitrarily. And so this is what gives us our unclonability. So going back to the swapping distinguishing duality, Fourier extraction here, it just reduces to a measurement in the Fourier basis, which is just the distinguishing task. So our equivalence is a proper generalization of this duality. And we show that Fourier extraction is just the computational dual to the task of implementing the representation. And if you can do either one, then you can do the other. So finally, how do we build quantum lightning? We use a specific type of representation known as a group action, where the group G acts by mapping between different set elements of the set X. So if you like, you can think of the set as a set of valid configurations of the Rubik's Cube, and the group as a set of moves. And the group acts on the set element by sending it to another set element. And for cryptographic applications, we always assume that there's some fixed starting point, let's call it X, from where you start acting with the group, and that every pair of elements has a unique mapping between them, but that it's hard to find. So, as I said, an action maps a set element to another set element, but since there's a unique starting point, we can express any set element relative to that starting point. And if we look at the output, we see that the action applies the existing group element, applies the group element on the existing group element to the left. So it's like a post-scrambling. On the other hand, a pre-action does the same thing, but acting on the right. So it's like it's a pre-scrambling. Imagine I scrambled the Rubik's Cube and then gave it to you and asked you to apply a certain set of moves before my scrambling. It's generally a hard problem, as you can imagine. And finally, a by-action is just both of these together. So pre-action security has a search and a decision version. And the search version is just the hardness of implementing a random pre-action. And the decision version says that it's hard to distinguish random actions from random by-actions through an interactive security game. And for those of you who are keen-eyed, you'll notice that this only makes sense for non-Abelian groups, since whenever they commute, the pre-actions are the same as the actions. So we really need the non-Abelianness here. All right, so the banknotes are just any state that's fully within an invariant subspace of the action. And the serial number is just the label lambda. And if you want to be technical, the banknote state looks kind of like this, with a superposition over all configurations reachable from the starting state. And the weights, these row lambdas, these are just weights that are essentially the matrix elements of the unitaries that appear in the blocks. So for example, if you use the cyclic group, you'll get coefficients that look like this, with phases that depend on lambda and the group element. So to verify, just perform any Fourier measurement to get the lambda. And to mint, just do the same thing, but on the starting point of the action. And it's easy to show that any configuration is a superposition of different banknotes, since all the banknotes form a basis. And specifically that the starting point, so if you set G here to be the identity, it can be essentially expressed as a uniform superposition of all the valid banknotes. So if you measure, you'll just get a random banknote, which is exactly what we want. And we show that the group action, we show that if the group action is pre-action secure, then this is a secure scheme for quantum money and quantum lightning. So looking forward, I hope that this leads to more investigation of quantum lightning and maybe even stronger objects, and to finding more cryptographic applications of the duality, of pre-action security, and of non-Abelian group actions. And you can take a look at the paper for some additional results that I haven't had time to explain. And with that, I'll thank you for your time.
Thank you, Barak, for this inspiring talk. Do we have any questions? Yes, please.
Thank you for a very insightful talk. My question is, with the Fourier extraction circuit, it seems that the Schumacher compression can be efficiently implemented.
Sorry, it's hard to hear. Can you?
With the Fourier extraction circuit, the Schumacher compression can be, it seems that Schumacher compression can be efficiently implemented. Is it correct?
Oh, I'm not sure. I'm not too familiar with Schumacher compression, but that would be interesting to see if there's a connection there.
Okay, thank you.
Okay, any follow-up questions? Maybe I can ask a question in the meantime. So since quantum token always requires a quantum memory in one form and another, I was wondering about your quantum lightning of I candidates. How does it work with those? Do they also require quantum memories in general? So can you somehow avoid those?
So it's a good question. So the question is, the quantum money often requires quantum memory, and that's something that's, like, I guess, very difficult to do. So does quantum lightning and quantum fire require memory? And in fact, it's quite inherent that they do. In fact, quantum fire in some way can be seen as kind of like a quantum advantage for memory, because it says that these are quantum states that, despite like being clonable, you can clone as many times as you want, you really inherently need to store them as a quantum state. Right? The moment like you store it as some classical string, the moment like you no longer have this quantum memory, this the quantum fire state is gone. You can't recover it. So in some sense, it's kind of like a quantum advantage for quantum memory. If you have quantum memory, you could implement these quantum fire states, but you really inherently need that. So yeah, I admit this is not necessarily a near-term thing, but hopefully the experimentalists here will figure this out sooner rather than later, so we can actually implement it.
Certainly. Are there any other questions? Yes, please. And then this.
Thanks a lot for the very nice talk, and especially for the amazing slides.
Thanks.
So I have just a small question about the assumptions you need. So on your last slide, you write that you use some group action on the related to the McEliece crypto system, so that's a public key assumption. And maybe it's intuitive that you would need a public key type assumption. But is it clear that that's necessary, or do you have any intuition that it should be for pre-action security?
Oh, it's a great question. So the question, I guess, is this McEliece crypto system is a public key assumption. Is it kind of inherent that you need some public key assumption? Is that the question? Is that right?
Exactly.
So yeah, for quantum money in general, it's not clear if you need if you need it for like the basic mini scheme of quantum money. For the full scheme, you definitely need public key assumptions, but for the mini scheme, it's possible that it's even way weaker than one-way functions, possibly even. So maybe we don't really need one-way functions to do quantum money, which is, I think, crazy, the fact that we don't really know that much about it. There's so many open questions about like what complexity you need for quantum money. But for this specifically, for pre-action security, it's inherent that you need some kind of one-way function at least. Whether you need public key assumptions, not for the. I'm not sure. I don't think so for. At least I don't know for the plain version. But if you want some kind of trapdoor version where you can make this efficiently verifiable, then I think you do need some public key assumption.
That makes sense. Yeah. Thank you.
Thanks a lot for the talk. I was curious whether if you have like quantum lightning or quantum fire, does this automatically also give some proof of work or proof of quantum space? Can you say that if someone has this fire, they need at least this much memory, or doesn't that automatically follow from your construction?
Oh, so the question, I guess, is like, can you use this quantum lightning or quantum fire to say that like if someone has these, then they have at least a certain amount of memory? So in some sense, yes, because well, they need at least something that's like super logarithmic, because otherwise, if the state is logarithmic, you could just like sample it as many times as you want until you accidentally come across the fire state or the lightning state. But I'm not sure if this is what you're asking for. But if you're asking like you're asking for proof of work as well,
or proof of space.
Or proof of space. Okay.
Proof of quantum space.
Proof of quantum space. Yeah. So in some sense, yes, it like shows that if someone has these quantum fire states, you necessarily need to have some quantum memory. Right? Does that answer your question? Yeah.
Sure. Yeah. I was curious if you know that cannot be compressed or anything from.
Oh, yeah. So I mean, I'm not sure, but it's a good question.
Thanks.
Okay. Thank you very much for your talk and your answers. So let's thank the speaker again.